Hi, welcome to Inside Out Math. This video is a lesson on surface area. Right now we'll just be deriving the surface area to a multivariable function by applying a double integral, and within the double integrals we'll also be doing partial differentiation as well. So before you proceed, please have a foundation in both of these things. So before we get started, let's recall a previous section where you learned a special case of a surface area, and it was surface area by solids of revolution. Surface area by solids of revolution. If I can spell. Okay, and I'll go ahead and illustrate it for you, and we'll draw some arbitrary function. And the formula was different depending on whether you rotated it about the y-axis or the x-axis per se. And the idea was you form a solid. Let's say if we rotate about the x or the y-axis, we get the area of the three-dimensional shape. And we'll define it by the area. If we rotate it about the y-axis, we'll define the surface area to be the integral, well, 2 pi times the integral from a to b of the square root of f of x, or f prime of x, quantity squared, plus 1 with respect to x. Or if we rotate it about the y-axis, or actually the x-axis, it would be 2 pi times the integral from a to b, square root of f prime of y, quantity squared, plus 1 dy. Now let's go ahead and define the surface area of a multivariable function, say f of x, y, and we'll define it as the area of S equals the double integral over domain D of the square root of the partial derivative with respect to x, quantity squared, plus the partial derivative with respect to y, quantity squared, plus 1 times dA. Alright, let's get into the proof now. Proof. So we'll start by drawing a surface I'll call S. And the idea is we want to split it up into infinitesimally small squares on the surface. And okay, these are supposed to be infinitely small, just like when we do integrals with rectangles. Alright, scroll down a little bit. And draw some axes. Label my axes, say x, y, and z. Now what we're interested in is just the area of one of these squares here, and then we generalize it to the whole surface. Now within this square here, I'm going to label a point closest to the origin, say I'll call it point P. Okay, and at this point here, we'll draw a tangent plane that will just kiss that point. Good. Now this tangent plane is an approximation to the surface, so this tiny square, or rectangle I should say, is an approximation to the area of that small little rectangle on the surface. So for this rectangle on the tangent plane, we're going to go ahead and project it down into the xy plane, like so. That's pretty good. You can imagine that in the xy plane it also forms another rectangle, and where's 3? I'll call this little bit of area delta A for the change in area. Since this green area is supposed to be infinitesimally small with dimensions, since we have a y-axis here, this is delta y by, and we have the x-axis here, we'll call this delta x. So delta A is delta x multiplied by delta y. Now, what's happening up here, one might ask? let's go ahead and take a closer investigation. Let's go and scroll down here. So now what we're interested in, again, is the area of this small rectangle on the surface. Okay, is this area here. Now the approximation to that is this parallelogram on the tangent plane. That's not quite a parallelogram, that's okay. And here I'll label this as this is point P there. Now if you've taken a course in linear algebra, you'll know that the area of a parallelogram is the magnitude of a cross product between two vectors. I'll label some vectors here. I'll call this vector A, and I'll call this vector B. Okay, and we'll call this red area here, I'll call it delta T for tangent plane. Okay, and it'll be the magnitude of the cross product between A and B. Now, if you refer back to a section on partial derivatives, you'll know that the components to this vector A will be delta x, 0, partial f, partial x, delta x. Okay, and B will be components 0, delta y, partial f, partial y, delta y. And we'll want to take a cross product doing the determinant, y. And computing the determinant. That should be a negative, sorry. Now it looks like I can factor out these delta x, delta y, but what is delta x, delta y again? Well, if we refer back to our diagram here, delta x, delta y is delta A, the change in area. Since this area is supposed to be infinitesimally small, we'll go ahead and factor out delta x, delta y, and we'll get the vector negative partial f, partial x, negative partial f, partial y, 1 multiplied by a factor of delta A. And so this is the cross product between vectors A and B. What we want is the magnitude of the cross products, and we should get the square root of partial f, partial x, quantity squared, plus partial f, partial y, quantity squared, plus 1 multiplied by, oh, not dA yet, but a delta A, since this is a discrete case. Now this is the area between, this is the area of one of the parallelograms. Now if we wanted the area of that whole rectangle, I should say, this again, this is just the approximation, we'll take a double sum, let's say as k equals 1, k equals 1 to m and n, and we're going to take infinitely many rectangles of the sum, double sum I should say, partial f, partial x, quantity squared, plus partial f, partial y, quantity squared, plus 1 times delta A. Now for the continuous case, we'll have the area is the double integral over the domain D of the square root of partial f, partial x squared, plus partial f, partial y squared, plus 1 dA, which is dy dx, or dx dy, whichever one you prefer. And here is the proof. Now, another thing I want to make a correlation with is arc length. Okay, and if you recall back to the definition of arc length, say in R2, we say that the arc length is the integral from a to b of, let's say, 1 plus dy dx quantity squared with respect to x. Now what does that look like in the xy plane? Well, we'll look at the R2 plane, and we're simply just finding the length of this curve, say A to B. Alright, now looking at R3 this time, let me just draw some axes here. I'll draw the same arc I drew in the picture above. So let's say it did this. But now, what is arc in R3? Well, since it's a multivariable function, we're going to this thing will extend out here. And let me just draw. We'll have something like this. Just like that. And what we're interested in is the area, not length this time, but area of the single, let's say, curtain. Up next will be a couple of examples.